Let's draw Lewis dot structures for certain molecules. It's a lot of fun to do that, okay? Now, the first thing we need to do to draw these structures is to identify the number of valence electrons, okay? And we've talked about these valence electrons in our previous videos, but this is such a central concept, so just let's quickly recap. Valence electrons represents the number of electrons in the outermost shell, okay? And if we bring up our periodic table, then the valence electrons for all the elements belonging to a particular group is given this way. So the first group will have, the elements of the first group will have 1 valence electron. The elements of the second group will have 2 electrons in its outermost shell, 2 valence electrons, and so on and so forth. When it comes to group 18, helium is an exception. It has 2 valence electrons, but the rest of them will have 8 valence electrons, 8 electrons in its outermost shell, okay? And just to get a sneak peek of why this is the case, here are some structures of some of the elements. You can see hydrogen, 1 electron in its outermost shell. Lithium, 1 electron in its outermost shell. Sodium, which has a total of 11 electrons, but 1 electron in its outermost shell. Same thing will continue, okay? But what about the elements of these groups? What about their valence electrons? Well, we don't have to worry about them because we're drawing structures for molecules that are formed by covalent bonds, meaning bonds formed by sharing of electrons. Now, metals, which I've drawn in red, okay, they usually do not participate in covalent bonds, okay? So it's only the non-metals that usually do that, and the non-metals are in green. And you can see all the valence electrons for the non-metals, we already have them. So we only got to worry about them and not worry too much about these, okay? All right, with that recap, let's now draw the Lewis structure for hydrogen. So the first step is, how many valence electrons does hydrogen have? It has 1 valence electron. So let's write that, 1 valence electron. And now, hydrogen would love to have 2 electrons because it'll make it stable in its outermost shell. And how do I know that? Because if I look at helium, look, helium has 2 electrons and it doesn't bond with anybody because helium is stable. All noble gases are stable. That's how I know hydrogen would love to have 2 electrons in its outermost shell. Now that means it needs 1 more electron. And here's the thing, if it needs 1 more electron, it's going to say, hey, I'm going to share 1 electron. If you need 1, you share 1, okay? So hydrogen says, hey, I'm willing to share my 1 valence electron. So it's going to share 1 electron. And if somebody else is willing to share their 1 valence electron, it's going to form a nice bond with them, okay? That's why it forms a bond with itself. And so now we can draw the structure this way. So here's the hydrogen, and here is the valence electron, and it's ready to share that. Here's another hydrogen. Here's the valence electron. It's ready to share that. And look, they're going to form a bond. This is called the covalent bond, and by sharing, each atom has access to 2 electrons, making them both stable. That's why they stay together. Okay, covalent bond. How do we draw the Lewis structure, the final structure? Well, we're just gonna represent this bond with a single line. So a single line represents a bond between 2 electrons. Okay, this is the Lewis dot structure for hydrogen. Okay, let's take another example. Let's take oxygen. If I go over here, oxygen has 6 valence electrons. That's where we start. Oxygen has 6 valence electrons. And how many does it need to attain stability? Well, if you look at neon, then you can see that it has 8 electrons in its outermost shell. And I know neon is very stable, so that helps me understand that 8 electrons in the outermost shell gives you stability. In fact, that is the case for most other elements. For hydrogen, it's 2, but for most other elements, they require 8 electrons in its outermost shell. We call this the octet rule. All right. So since oxygen requires 8 electrons in its outermost shell, it has 6, so it needs 2 more. If you need 2, you share 2. That's the rule, okay? So it's going to share 2 electrons. And if somebody else is willing to share their 2 electrons, it's going to form a bond with them. That's why it forms a bond with itself, okay? So how do we do that? Well, again, we're going to draw 2. So we're going to draw the Lewis structure. We're going to draw 2 oxygen atoms. And now, since it has 6 valence electrons, here's how I show the valence electrons, okay? 1, 2, 3, 4, 5, 6. Why do I draw it this way? Because just by drawing it this way, again, you can see just from the dot structure that there's 1 pair, there's a second pair. Oh, there's no pair here. Oh, there's no pair over here. These electrons are lonely. They want to get paired. And that's how I know that these 2 electrons are going to participate in bonding. It's going to be shared. So just by looking at the dot structure, I can see that it's going to share 2 electrons. That's another way to just confirm the same thing that we got over here, okay? So it's going to share these 2 electrons. This oxygen atom is going to do the same thing. 1, 2, 3, 4, 5, 6. it's going to share these two, which means these two electrons and these two electrons can form a bond. Now, just to make it a little convenient for me to draw this, I'm going to show the lonely electron here. I'm going to show the pair over here. You can draw the pair wherever you want, okay? It just makes it so much convenient to draw bonds over here. So this means these two electrons are going to form a bond over here. And these two electrons are going to form a bond over here. And there you have it. That means oxygen is going to form a double bond. And you can count the number of, because of this covalent bond, you can count the number of electrons each oxygen has access to now. If you look at this oxygen, it has 1, 2, 3, 4, 5, 6, 7, 8. It has 8 electrons access to it. And this oxygen, 1, 2, 3, 4, 5, 6, 7, 8. It has also 8 electrons access to, and so octet rule is satisfied. And so now, how do we draw the final Lewis structure? Well, here's the oxygen atoms. 1 and 2. So 2 bonds, 2 lines, and then we have to show the lone pairs. These are called lone pairs because they do not participate in bonding, but it's important to show them. So here's the lone pairs. You can show the lone pairs wherever you want, okay? But do show them in the Lewis dot structure. And there you have it. That is the dot structure. All right, your turn. Why don't you try drawing a Lewis dot structure for N2? Why don't you pause the video and give it a try? All right, here we go. Again, I look at nitrogen over here, and I know that nitrogen has 5 valence electrons. That's where you always start. Number of valence electrons. And octet rule, remember, most elements follow the octet rule, so it requires 8 electrons in its outermost shell for stability. It has 5, so it needs 3 more. If you need 3, you share 3. So it shares 3 electrons, and again, if it can find some other atom or elements that can share 3 electrons, it will happily bond with them. That's why it forms a bond with itself. And so how are we going to show that? Well, same way. So we're going to draw the 5 valence electrons over here in the same way we wrote it over here. 1, 2, 3, 4, 5. And again, you can see just by drawing the dot structure, we can see there's 1 pair over here, but there are 3 lonely electrons which would love to participate in bonding. That's why it shares 3 electrons. Just by looking at the dot structure, you can confirm that. Same thing over here. 1, 2, 3, 4, 5. So these 3 electrons can bond with these 3. And again, just to make it a little convenient to draw, okay, I'm gonna draw that pair over here, and I'm gonna draw that pair over here. All right. And of course, the more practice we get, the better we'll be at conveniently drawing them, okay? But anyways, now that we have these 3 electrons, they can form a bond with each other. And so bond number 1, bond number 2, bond number 3. So nitrogen forms a triple bond with itself. And again, if you count the number of electrons, this nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. And for this nitrogen, again, 1, 2, 3, 4, 5, 6, 7, 8. Octet rule is satisfied. So what does the Lewis dot structure, final structure, look like? Well, I have 3 bonds, so it's going to be a triple bond. And then do not forget the lone pairs. Never ever forget the lone pairs, okay? And this now explains why nitrogen loves to form 3 bonds, either a triple bond or a double bond with one element and a single bond with another element, or 3 separate bonds. And oxygen, for example, loves to form 2 bonds, double bonds with another atom or 2 single bonds. All right, let's kick things up a little bit. How about we draw one for water molecules? Things are going to get interesting now. The idea is the same though. You start with the number of valency electrons for each one, and then think about how much they share, and then try to form a bond. Now, of course, because you have 3 elements over here, there could be a little bit confusion about how they're all connected. The general rule is the element which is on the leftmost side of the periodic table. Again, if here's a periodic table, look at the one that's on the leftmost side, which is least electronegative, or you can also think of it as most metallic, because all metals are on the left side, right? So the one that is on the leftmost side will usually be the central atom. All right. What about hydrogen? Hydrogen is the leftmost, but it is an exception. All right. So hydrogen will always be on the side. So except for hydrogen, any other elements that you have to consider the one that's on the leftmost side. That will be your central atom. We'll take more examples. It'll make sense. But at least when it comes to water, since hydrogen will always be on the side, the oxygen will be in the center. So we can immediately draw the structure. So the oxygen will be in the center. The 2 hydrogens will be connected to it. And we already know their valence electrons and how much they're going to share. So I'm going to write one for oxygens. I'm going to start with that. Same technique. 1, 2, 3, 4, 5, 6. So it's going to share these 2. and hydrogen just has one. And so you can kind of see these two are going to form a bond with these two. And again, just for convenience, what I'm going to do is I'm going to take this and put that pair here so that I can nicely bond these two. And there you have it. So this is going to be bond number 1, and this will be bond number 2. And that's it. That's the structure. So dot structure. So it's going to be oxygen, hydrogen, hydrogen, one bond here, one bond here, and do not forget the lone pairs. Okay, again, your turn. How about you draw one for NH3? Pause and try. All right, there are 4 elements over here, but again, because hydrogen will always be on the side, we know it's the nitrogen which is going to be the central atom, and the 3 hydrogen will be connected to it. So nitrogen will be in the center, and the 3 hydrogen, well, we can draw the 3 hydrogens wherever we want. So let me just draw them over here. And again, we'll start by drawing the valence electrons on the central atom. So 1, 2, 3, 4, 5. I know it has 5 valence electrons. So where do I draw them? I'm going to draw the 5th one over here. You can see that, right? Now I can conveniently draw the bonds over here. And 1 valence electron for hydrogen. It's ready to share that. So 1 bond over here, 1 bond over here, and 1 bond over here. And this will be the lone pair. And again, you can check. Hydrogen has access to 2 electrons. Nitrogen has access to 1, 2, 3, 4, 5, 6, 7, 8. Okay. So what's the final structure going to be? Well, I have N, and I have single bond H, single bond H, single bond H. Am I forgetting something? Yes, the lone pair. Do not forget the lone pairs. All right, final challenge. Carbon dioxide. So carbon is a new element for us now. Why don't you pause the video, look at the periodic table, and try to draw the Lewis structure for this one. All right, since carbon is a new one, we need to think about carbon. Carbon has 4 valence electrons, and it needs 4 more. And therefore, so let me just write that down, 4 valence electrons. It needs 4 more. If you need 4, you share 4. Okay. And now is the interesting one. I don't have hydrogens. I have carbon and oxygen. How do I know which is the element that comes in the center? Well, again, CO2 might be simpler. You might be able to guess it, but we're going to look at which one is the leftmost element. And you can see carbon is the leftmost element on the periodic table. Oxygen is over here. Carbon is over here. So carbon comes in the center. All right. So carbon will be in the center and oxygen will be attached to it. So I'm going to draw 2 oxygen atoms over here. And now again, I can draw the Lewis structure for carbon. How do I do that? I'm going to show the 4 valence electrons. 1, 2, 3, 4. That's all there is. And look, they're all lonely. They're all 4 lonely, and therefore they're going to share all 4 of them to form pairs. And the same thing for oxygen as we've done before. 1, 2, 3, 4, 5, and 6. Where should I draw 5 and 6? Well, let me see. I mean, we can draw it anywhere, right? So let me draw the 5 and 6 here. Okay. Same thing over here. 1, 2, 3, 4. I'm going to draw the 5th and the 6th one over here. So we can bond this and we can bond this and we can kind of bond this and we can kind of bond this. It's a little crooked, but it's okay. We get the idea across. So this is one pair and then we can bond it over here. And we can bond it over here. It's fine. It's fine. I know it looks a little weird, but we get the gist of it. Carbon is going to form a double bond with this oxygen atom, and the carbon is also going to form a double bond with this oxygen atom. And let's count. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. What about oxygen? 1, 2, 3, 4, 5, 6, 7, 8. And the same thing with this one. And so we can now draw a better Lewis final structure. So carbon, oxygen, oxygen, 2 bonds. So double bond here, a double bond over here. Do not forget the lone pairs. So there are 2 lone pairs over here. Let me draw them over here and here. And there are 2 lone pairs over here. Are there any lone pairs on the carbon? No, there are no lone pairs on the carbon. So there you have it. That was fun, right?